Hello everyone, in this short video you're going to learn about mesh study in Abaqus, one of the important steps in each FEA simulation. Before running any simulation, you have to simply ask yourself a question: how do you achieve an accurate result while balancing the size and solve time of a FEA model? You might have a simple model and you can quickly get a result. How do you know that your result is correct, and why this is important? Numerical software package solves a problem using a series of discrete points. Each point or node adds a degree of freedom to the system. So the more degree of freedom in the model, the better it will capture the structure behavior. However, if you have too many degree of freedom, the model could take days to run. And if you have too few degree of freedom, and the response could be inaccurate. So there is an optimum points of element number. That's why it's important that we do a convergence and mesh study. Mesh convergence determines how many elements are required in a model to ensure that the result of an analysis are not affected by changing the size of the mesh. After doing a convergence study, we have to check that if additional mesh refinement does not affect the result. And once we do these two studies and we are 100% sure, then we can carry on with our simulation. To show you the example, I created a simple geometry. So what I have a beam here, circular shape beam, and what I did, I basically fixed one side and applied the force in negative z direction. So if I click on this one, you'll see that I created this load which is -1000. Okay, and so in the next step in the mesh, I have a different size for each of these beams. So I started from 8 to 1, and for instance, I have 8, I have 6, 4, 2 millimeter, and 1 millimeter. So I want to know that what is the optimal mesh size for this simple geometry, and I created a job. So you can find this file from the resources section, in order to see this one, you have to run a simulation. So I've already run this simulation, but you can pause the video and submit a job. And once you get the result, then you can carry on with this video. But let's just see this result one by one. So if I click on 8 millimeter, you'll see that I still got the result. The mesh is very coarse, and as you can see, I can see these. The curvature is not actually a circle due to a lack of number of mesh, but still I got a result. But how do I know that if this result is correct or not? So we have stress, and also we have displacement. One of the way of doing this is to basically record the number of the elements and also the displacement, maximum displacement. So I created this Excel file. So I have this Excel file. So when I have 8, the element size is 8. The number of the element is 962. So I'll show you how you can actually see the number of the element in Abaqus. So if you go to mesh section, and I'm going to go to 8, and then if you click on query information, you can go to mesh, and then click on done. And at the bottom here, the Abaqus will give you a total number of the elements, which is currently 684. Okay, I don't know if so this is total 684. That was the total number of nodes. And then also you get at the top the total number of the nodes. So when you do a stress mesh study, you can either use the number of nodes, or you can use the number of elements. So what I simply have done in the x-axis, in both these curves, what I have a number of the element. And as you can see, when I decrease the element size, the number of the element increases significantly. So see the difference between an 8 millimeter mesh size and 1 millimeter mesh size. So here we have 684 elements, and here we have 35,000. And this is just a simple model. So it's just a very simple circular beam. You could have a complex geometry, and changing from 8 to 1 could increase the number of the mesh with 1 or 2 million. So you have to really be careful to choose the correct mesh size. In the y-axis, what I have done, I have selected the max displacement. So I recorded the max displacement for each of these simulations. So as you can see here, if I see the result here, and if I go to displacement, and we have the magnitude of that is 5.72, that we have it here. And I did the same thing with the other one, like this. If I go to here, so you see this one is 5.4 times 10 power minus 3. So I did for all of these, and I got these curve that you can see here. I'm going to just make this one bigger. So what I have a number of the elements, and I have the maximum displacement, which is in, it's going to be in millimeter. And there should be a E minus 3, which is basically I didn't include this one in this number, so to make it more clear. So for 8 millimeter element size, the number of the element is 684, and the displacement is 5.72 times 10 power minus 9, minus 3 millimeter. But when I decrease the element size, you see that the displacement drops significantly. But after a certain point, it reached to a plateau. As you can see, the displacement from, for instance, 4 millimeter, which we have 2,500, no, let's say this one, from at 2 millimeter, which we have 9,000 elements, and up to here, it doesn't really change much. So that means that this area are a suitable area for selecting your element size. So if you're going for any number, so this area that we have is basically the optimum area for selecting mesh. Obviously you cannot go, you don't want to go for the last one, and the reason is that you have to check the CPU time. So when you look at the CPU time, I could solve the first bin with the element size of 8 millimeter in less than a second. However, when I decrease the element size to 1, you see that the CPU time increased significantly from less than a second to 190 seconds. And as you can see, the difference between a result is not significant. So here the displacement is 4.98 and here is 4.95. So I don't gain that much accuracy by decreasing the element size. But on the other side, I increase the simulation time by at least 8 times, roughly 8 times. So this is a thing that you have to avoid. You have to find the optimum part. So if I want to run this simulation, I would be happy with this value. So this is even 3 millimeter could be an option as well in this simple example. So when you do a simulation in future, you have to make sure that you definitely have to do a mesh study. So when you have a complex geometry, you don't want to increase the CPU time, and also you don't want to have a wrong result. So you have to find that optimum point that you normally can get that plotting these maximum displacement and the number of the element. So you get this plateau curve, and you select your mesh size in this region. So you and again, you don't want to be toward the end because you have the higher CPU time. Somewhere around this, somewhere around here, will give you the accurate result. Okay, I hope that you enjoyed this short video, and if you have any question about mesh study, please let me know. Thank you.